Hello everyone, and welcome to the SIA project. SIA stands for Secondary Injury Avoidance. During the initial disaster response phase, it is imperative that first responders are armed with all the appropriate information necessary for them to manage any rescue attempts while also maintaining their own personal safety. SIA is a semi-automated solution for information gathering. The system can be used in populated areas affected by natural disasters or crime. The robot swarm can be deployed to gather the initial scene data, helping to reduce the risk of injury to first responders due to secondary factors such as unstable debris piles, fire or flooding hazards, toxic gas hazards, and the system will even transmit the location of human casualties when encountered while mapping the area. The target demographic for the SIA system will be anyone tied to the initial response wave following any sort of disaster circumstances. Secondarily, however, the system will also benefit policymakers running on platforms of protecting the private citizens as well as the private citizens who encounter the system while in live operations. For the design requirements, it was imperative that the robots were able to relay all necessary information in a timely and accurate manner, not be too cumbersome and able to adequately maneuver through treacherous zones, safely operate without causing any harm to people or further damage to property, and it must be able to navigate and perform its assigned function without the need for human input.
All right, so for slide one of the mechanical design of the MWTB, we have everything identified in the profile and side view. We've got blue parts, which are mechanical. We've got orange parts, which are electric. As you can see, we've got the wheels taken off here. The wheels are buoyant to make the vehicle amphibious, and we've got axles here and a gearbox with an Arduino unit and a DC motor. Now the sensor array we have is a moisture sensor, IR sensors, and pressure sensors. These are for navigation. These are for locating people, and these are for locating the presence of flooding. We have an LED up here too, just to let everyone know of its presence. Rescue basket design. Eyelet for airlift, couple fenders to keep people safe and satisfy the requirements, and we have a rubber bumper here, so when we hit stuff and or people, it'll be okay. We're going to continue on through the second slide. As you can see, we have an opening of the gearbox here showing the chains and gears that power the drivetrain, actuators once again, and sensors once again. We've already discussed these, so I'm not going to go into this much further. As we continue, we've got the circuit design. Sensors, actuators, and other electrical parts are organized by color, and we'll just go through them. We've got a PIR sensor in place of the IR sensor because the IR sensors in Tinkercad do not provide the opportunity for detecting thermal signatures of people. This works pretty good. We've got an RGB LED to indicate the successful transmission of a person being detected to the central hub. Pressure sensors for navigation, one on each side. We've got resistors, H-bridge driver, 9-volt battery, which would actually be a larger capacity deep cell lead acid for quick replacement. Arduino, obviously. DC motors, which would be our actuators here. A white LED, as was seen in the mechanical slides design, and an orange LED, which suggests the successful transfer of flooding conditions to the central hub. Logic flow chart is as follows. We're detecting several things. One, we're detecting people, water, and force. This is the navigation. If we hit something on the left, we're going to reverse and turn right. The opposite occurs if we hit something on the right. And if we hit something on both sensors, which would be a direct hit, we're going to reverse a little bit longer. Everything else is the same though. Moisture sensor, we detect moisture. Well, is it flooding? Well, if it's above 78%, we're going to assume it's flooding. Turn on the orange light and report it to the hub. And if we, continually receive stuff that's not 78%, we're still going to have that light on, just to let everyone nearby know. The hub sends data. What kind? Fire. We're going to avoid it. Gas. We're going to avoid that too. And the reason is because we might be transporting people and or goods that are important for the rescue operation. We're always going to report individuals, but we might not necessarily pick them up. And you'll see why that is later. All right, we have the Arduino code here. If you want to pause this and look at the individual functions, they are labeled by 2 forward slashes. Now we're going to go through a demonstration of the Tinkercad Arduino design itself. Here, as you can see, we have started, and it follows a logical flow chart in that it has begun proceeding forward with the white LED flashing. This is important to indicate location for everyone around. We have a PIR sensor, like I said, in place of an IR sensor. As you can see, we're going to simulate finding someone. As you can see, the RGB LED is indicating an array of colors based on the programming, and it's successfully transmitting that location to the central hub so that other robots can respond, clear the area, and then individuals and or the MWTB-01 can rescue them. We also have a water sensor down here, our good old moisture sensor, and that's going to detect flood-like conditions. Upon it reaching 78%, it'll report that to the hub. Otherwise, it may just suggest, maybe we have a sprinkler broke or something like that. It's unlikely that would be particularly dangerous to the bots in our swarm and people. However, if there are flood-like conditions, that could be dangerous to children, and it could be dangerous to thermocheck, which is not an amphibious vehicle. Successful transmission of flooding conditions is indicated by the orange light. As you can see, we're moving forward, searching and mapping. And if we encounter an object on the right, it's going to reverse. Then it's going to turn left. Of course, the opposite is going to happen here. Once pressure is gone, the opposite is going to happen on the left if we encounter an object, and I'll demonstrate that real quick. Now the other option is, we hit something and it, affects both sensors. Well, I couldn't move both sensors at once, so you're going to have to bear with me. It's going to indicate a left strike first, but it will indicate a right strike as the if-then conditions make presence known for both sensors. We're just going to reverse a little bit longer to fix that. All right, and there's the code.
I'll be presenting ThermoCheck by Matthew Felber. On this slide, we can see the CAD rendering of my robot. I chose to design it out of 3/16 stainless steel sheet metal. All exterior surfaces are 5/16 of an inch thick for optimal heat shielding. The robot includes oversized tires protected by shielding on the sides to allow it to traverse the vast majority of obstacles. In the first slide on the left, we see the heat sensor and LED as well as an Arduino Uno and battery inside of the robot. I will mention, however, that the void would typically be covered with an ultrasonic distance sensor placed on top, but due to availability of the slide, it is open for this presentation. While lightly difficult to tell, we can see in the far right image one of the twin DC motors connected to the rear wheels. Throughout the design process, the robot has stayed the same except for adding 2.5 inches to the overall length to allow for better fitment of the tires. On this slide, we see the circuit and schematic of the design. Both the temperature sensor and ultrasonic distance sensor are connected to the DC motors to control forward movement and prevent damage. Both DC motors are controlled by the bridge, which is in turn connected to the Arduino. All functions, however, are directly controlled by either the ultrasonic distance sensor or temperature sensor. In this slide, the overall flowchart directly follows the code and commands. First, the robot runs a temperature check and sends information to the hub. If the temperature exceeds 325 degrees, the drone will halt and alert emergency response. More to come with that on the next slide, however. After ensuring the temperature is of acceptable degrees, the robot continues forward using its ultrasonic distance sensors. If an object is detected within 10 inches of the robot, it will inform the robot to stop and send information to first responders. With the program on the right, an if-else command is being used to identify if it is safe for the robot to proceed forward without running into potentially harmful debris. If the robot detects an object within 10 inches, it will immediately halt forward movement and notify first responders. On the bottom left picture, we can see the temperature being displayed as well as an obstacle warning and forward movement halted. The code on the right displays the active temperature. If the temperature exceeds 325 degrees, the robot will alert emergency response and halt the drone. A display will also inform, similar to distance, the reasoning for stopping, and the drone as not to confuse first responders with what danger is possible ahead.
Hi, my name is Daniel Massengill, and I'm going to be presenting HG1. The HG1 has a specialized track assembly that allows it to operate on both land and water. For directional capabilities, an ultrasonic distance sensor is used to control 4 DC motors. When an object is within 12 centimeters of the robot, the DC motors will reverse course on one side and turn the robot in a new direction. The HG1 circuit assembly is comprised of an Arduino Uno, gas sensor, a 9-volt battery, L298 motor controller, 4 DC motors, an ultrasonic sensor, and an IR sensor. As previously mentioned, the ultrasonic sensor is used to control the 4 DC motors for directional movement. The IR sensor and the gas sensor, when receiving a signal from the environment, will transmit a location signal back to the controller to notify first responders. Starting on the left-hand side of the flow chart, let's take a look at the IR sensor circuit. We can see that on pin 8, once the output signal is set to high, that is going to trigger an action of turning on the LED light, as well as automatically sending a location signal back to the controller. In the middle of the flowchart, we can see the ultrasonic sensor and the DC motors. When an object is less than or equal to 12 centimeters, that is going to trigger an action of delaying the motor output on one side, which will effectively turn the HG1 robot away from the object and allowing it to continue on its path. On the right-hand side, we can see that if the gas sensor value exceeds the preset value of 35, it will automatically send a location signal back to the controller to notify the first responders of the hazardous area.
As we proceed, you can see we have a collective behavior flow chart here. This is the hub connecting to the swarm and collecting data. We receive fire data from ThermoCheck, person data from all of them, mapping data from all of them, flooding data from MWTB01, and hazardous gaseous data from HG1. What happens is we create a visual depiction. We note on that the conditions of these, the location of these other conditions that could be dangerous. And if we find a person, we want to make sure that before I go there to save them with my MWTB01, there are no dangerous conditions. The swarm's pretty innovative. It has sea and land capabilities to the extent that it has amphibious vehicles in it. We have airlift potential, which could be important for sea and lake rescue operations. And it's a collective swarm in that not only are we accomplishing one goal, but each of us has an individual aspect of how we are working together to keep the area safe by detecting various things such as mapping, people, fire, gas, and water. All of the customer requirements and/or criteria are satisfied. The operation time is basically limitless with replaceable batteries. All units move pretty quickly. Maneuverability is particularly enhanced with the smaller units, and speed is enhanced with the MWTB01 based on its large wheels. Cost is effective in that it's not going to cost too much and that we're using readily available parts.
The SIA system is relatively affordable for the average city response unit. With a total price of nearly $4,500, with robots and drones becoming more popular by the day, an array of companies have entered this emergency response space. While none have directly made a hub centralized response, many have gotten into wildfire surveillance as well as a single-person autonomous transport drone. Additionally, FLIR has released a drone capable of detecting an array of gases in the field. Why would one choose SIA? With a diverse range of emergency response possibilities and the centralized communication via robots to a centralized hub makes SIA the clear industry leader. Investing in an SIA product is guaranteed to bring you the highest quality design and equipment on the market, as well as having a readily available and easily replaceable parts on hand so your swarm can stay in motion.
So in summary, what we have here is a problem of people needing information that's objective and accurate. Subjective information can put people at risk, and SIA swarm reports to a central hub and to the first responders only the objective information, suggesting things that are actually happening. That information could be where humans are. And we use state-of-the-art, budget-friendly, life-preserving systems to make that happen, and also detect the presence of fire, toxic gases, and flooding like we've discussed before. If I were to do this again with this team, I think we would all probably start with a Gantt chart. It's very effective in terms of timelines. We would set limits on virtual meetings. Those can seem to get long sometimes. Create a physical circuit. That would be more of a hands-on approach and probably feel more gratifying, but we'd start coding earlier as well. In terms of gratification, learning what we learned in this class and applying it firsthand is very gratifying. We have a lot of doctrinal style courses in our life that we experience, and absent application to the real world, it's sometimes disheartening that we have to waste time in those classes. The technical trio also learned the benefits of effective communication and how, even over long distances, we can be highly successful